is to the to keep the highest value possible, so to say. It's like I said, it's very unique. There are a couple of installations in the world that can do that, and Umicore is one of those companies that can actually do that, and a crucial element, let's say, in the circular economy if it comes to metals. Chrisian already mentioned it before we started, but we have seen each other quite frequently in different meetings, and I'm always very impressed by the work that Umicore is doing. Chrisian is now the Director of EU Government Affairs at Umicore, and he will be talking about the work that they are doing and how they are basically a very important link in the circular economy. So thanks again, Chrisian, for joining us. And without further ado, I would like to give you the floor.
Yes, thanks a lot, René, for the kind introduction. And nice to meet you, at least again virtually, hopefully sooner or later also physically again. You see my screen, yeah, already? Okay, perfect. So actually, in my talk today, I will not talk so much about Umicore. There only will be one slide introducing the company, which will be the next slide. And then I will talk more about a little bit the fundamental requirements of becoming circular with a specific perspective on metals, and why, especially in those days, it's extremely important to really to move towards more circularity. And on the intro screen here, you see already a number of important and also emergent products. You see batteries for electric vehicles, you see smartphone tablets, and then you also see some components in these products like circuit boards and catalysts. And of course, it's a Photoshop picture, the one with the circuit boards with a gold and the palladium bar. Yes, there is some gold and some palladium in circuit boards, but of course not that massive as it is here. But let's start. So this is the only really Umicore picture to give you a brief overview what we are doing. So we are doing much more than recycling. Umicore is a materials technology and recycling group, pretty large, listed on the Belgium Stock Exchange. And we have three main areas of business, which are all linked to clean mobility and green products. So we are still one of the three major producers in the world of automotive catalysts, which of course are needed and will be needed for a couple of years for the traditional combustion engine, but of course also in hybrid vehicles you have automotive catalysts, and not to forget fuel cells. Also fuel cells, the PEM fuel cell technology work with a platinum-based catalyst technology. By the way, also for hydrogen electrolysis, you need catalysts, and this is a field where also Umicore is very active in. So this is the column number one. Column number two is battery e-mobility. There we are leading supplier of key materials for rechargeable batteries, specifically for cathode materials. And this is then linking to what René was mentioning in the introduction. We are not only manufacture such products, but we also have in Hoboken, close to Antwerp, a very large, what we call an integrated metals smelter and refinery, where we recover from a wide variety of different products, metals, and in this case, really metals back in a physical state. So pure metals, which are identical with metals which come from the mining side. And at the foot line of this slide, you see a number of chemical symbols of metals, and all these metals are in the Umicore portfolio, so they are important for the products which we manufacture, but most of the metals we also do recover in our recycling operations. And if you have a closer look at the chemical symbols, you see, yes, there are base metals like copper and nickel, but you also see a lot of special metals and of precious metals. Okay, I think many of you might have seen this graphic before, but it's really nice. It's not from me, it's from Armin Reller and his team from Augsburg University. but it nicely shows how over the centuries the importance of raw materials and metals for our daily life really has increased. And if you just compare the left end of the graphic with the right end, so on the left end you see a windmill from the early days, and in Holland, of course, you still can see a lot of these windmills, but technology-wise, they had been maybe amazing, but from the materials complexity, not that amazing. So you had a lot of timber and limestone or stone and bricks, and maybe some iron to reinforce here and there some things. And if you look at the windmill of today for energy generation, you find more or less half the periodic table of elements in the windmill, and this is not only valid for windmills, it's also valid for many other applications we have in daily life. And why is this the case? The reason for this is that, of course, raw materials and especially metals have very unique chemical and physical properties, and we need this properties to get certain functions of our products. And this can be quite nicely illustrated now just over a time span of some 100 years on how the complexity of mobility developed. So our early mobility, which is just 120 years ago, still was horse-driven by biomobility. Then already in the 20s, we had mass production of cars. See here the Tin Lizzie, but it was still quite simple. You had, of course, iron and steel. You had already lead for the battery. You had some copper for the wiring, but that's it. In the 50s, the cars became bigger and also more fancy. So we had all kinds of steel alloys, but also decorative elements. Think about this US cars from the 50s with all this chromium applications and so on. And then already in the 80s, the catalyst was invented, actually here in Hanau, where I'm located. And with the catalyst, we brought platinum, palladium, and rhodium into the car. And also the first rare earth elements, cerium and lanthanum, which are used as promoter also in an automotive catalyst. Around the turn of the millennium, we had more and more intelligence in the car. So think about all the auxiliary systems, electronics, navigation systems, brake assistance, and so on and so on. We also had much more focus on lightweighting. And with this, we brought additional elements, so all the electronic elements, precious metals like gold, silver, palladium, but also semiconductors, indium, gallium, germanium, and so on. And since a bit more than 10 years, we see a rising development of electromobility, and this can be two ways. So it can be battery electric, but of course also fuel cell electric, and with this then also come the battery materials. So if you compare a car of today, which you also could call a kind of computer on wheels, with a car of the 1920s, it's easy to see it's much more complicated. If you take the total car fleet on this globe, which is several hundreds of millions of cars, this in total represents a significant urban mine, so a potential source for recycling. But on the other side, a car of the 1920s or even of the car of the 1950s, it was relatively easy to recycle because it was not as complex as our cars of today. So if you want to recycle a car of today, this is not an easy task. So you need high tech, not only to manufacture such cars, you also need high tech to recycle it. And I'll come to this later. And this just very briefly, because this was just the example of cars, but what you find here in the table is a matrix of all kinds of applications from the wider field of high-tech and clean-tech applications, for medical applications, pharmaceutical applications, to technical applications. And then in the columns, you see different elements. And in this case, I left out the base elements, which of course are included as well, and focused on special metals and precious metals. And wherever you see a gray dot, this means that these metals are essential to produce these products. and you see a lot of gray dots. And for example, if you compare the catalyst line, which is marked with a red arrow, with the electronics line, you see that many of these metals are, for example, used in both, in catalysts and electronics, and by the way, also in batteries. And this also means getting access to these metals becomes very important, and there also could be some competition who gets access and who is able to pay a certain price for the metals. You certainly heard about the European Green Deal, which was published in 2020. And there are a number of measures included in the Green Deal, and I've selected here some which I framed in red, which have a direct or indirect impact on metals. This is on the one side, of course, one of the focal topics of the Green Deal, increasing the EU's climate ambitions for 2030 and 2050, then mobilizing industry for a clean and circular economy. This is one of the topics which is extremely important, of course, also for Umicore. Accelerating the shift to sustainable and smart mobility. A zero pollution ambition for a toxic-free environment. Here we have to see also if we use certain metals, certain raw materials, what side effects are connected with this. And linked to this, of course, is also mobilizing research and innovation. This Green Deal communication was from 2020, but I copied here one central part from this Green Deal communication, which in those days with this challenging geopolitical developments and the Russian invasion in Ukraine and all the effects it has also on our economy has been quite a very foresight statement, and I just read it out. Access to resources is also a strategic security question for Europe's ambition to deliver the Green Deal. Ensuring the supply of sustainable raw materials, in particular of critical raw materials necessary for clean technologies, digital, space, and defense application, by diversifying supply from both primary and secondary sources, is therefore one of the prerequisites to make this transition happen. So really in this Green Deal communication, raw materials, metals, and also circular economy are really at the heart of the whole strategic approach. And already some years before, in 2015, the EU published the so-called circular economy package. And again, I read here one central sentence from this, which says, circular economy is an economy where the value of products, material, and resources is maintained in the economy for as long as possible, and the generation of waste is minimized to develop a low-carbon, resource-efficient, and competitive economy. And on purpose, I underlined the last part because it clearly shows the link from circular economy to climate, to resource efficiency, but also to a competitive industry. And this means circular economy is not a target in itself; it has a purpose to fulfill. And in this context, of course, metals are, in principle, the ideal candidate because. And of course, this is in quotation mark, they are eternally recyclable. If you compare it with paper, with plastics, for example, usually for metals, you don't have a downcycling issue if you do it in state-of-the-art facilities. So you have no material quality issues. Recycled metals usually have the same physical chemical properties and also traded at the same prices as metals coming from mining. But, and also we'll come to this, of course, circular economy means much more than recycling. Recycling is just the last step in the circular economy, but also this step has to happen. What is important to understand, I will come back to this again in the presentation, is that if we talk about closing the loop, we have to close the loop really physically and not only on paper. This sounds trivial, but if you look in the legislation which we have today, in the waste legislation, we have all kinds of recycling rates which have to be met. But if you took a closer look at the recycling rates, and I will give an example for this, in many cases or most cases, this means not a physical closure of the loop, but it's more a kind of closing the loop by definition, meeting recycling rates by definition, but this doesn't help us, for example, in getting more supply security or really having a positive impact on climate mitigation. I mentioned that circular economy, of course, is more than recycling. This is a graphic we developed in the International Roundtable of Critical Raw Materials, where also René is participating. And it shows that the more circular we are, of course, it helps us a lot also in managing criticality. And we have different effects. Some of the measures, they have an impact on the demand side. So they decrease the demand, and other measures have an impact on the supply side. And I just listed it here. So of course, circular economy has to start already in the production chain and in the mining chain. And also here, there is still room to become more efficient, having higher yields in metals and so on. Then, of course, we need efficiency in product manufacturing and in certain areas in substitution, and this reduces the demand for critical raw materials. We need appropriate design of products and services to keep raw materials in the loop or keep them longer in the loop. And this again works on the demand side. Same is extension of product lifetime, including repair and reuse. At the end, we have to recycle to increase the absolute supply of raw materials, but also, of course, supply security, because our end-of-life products are in our backyard. We don't have to import them from Russia, for example, or from other parts of the world. And industry has to cope with this, and industry has to develop appropriate business models and also strategies to become as circular as possible. And for Umicore, this is a little bit in the genes of our company, because this closing the loop philosophy is not only since the communication on the circular economy, but we started with this already in the 90s of the last century. Why is recycling important? And I make this very quickly. Of course, it helps to mitigate the environmental impact of mine supply, so it improves the environmental footprint. And if you're talking about green products, of course, it's extremely important that the green products are not only green during the use phase, but green during along the entire life cycle. It prevents the impact from non-recycling. So if you go in landfill or deposit, it also has an impact on emissions, on land use, and so on. I think that the third bullet in those days is extremely important because recycling reduces the geopolitical dependence on few mining countries and or companies. It's also important to support ethical sourcing of raw materials. It can partly eliminate the supply risk of certain byproducts, coupled products. Maybe this is a bit complex for now, but we could touch it in the discussion if interested. And it also helps to mitigate metal price volatility because you just have a broader supply. So let's look in one example of a complex product. I had the car at the very beginning. I now take the example of a smartphone or of a tablet. So what you have here is what I call the complex multi-metal or multi-material assembly, and it has a complex mix of a bit the good, the bad, and the ugly. So you have the precious metals, you have base and special metals, but you also have hazardous substances like mercury, beryllium, lead, arsenic. Often you have halogens as flame retardants in the plastics, other organic materials, and so on. And this all is tightly interconnected in an assembly. So what we need to do here is a responsible recycling, like we need responsible mining. We also need responsible recycling to cope on the one side with the hazards while recovering the value. So we cannot just focus on recovering value and forgetting about the hazardous or the other way around. We really have to combine this. And in this context, you often hear the expression quality recycling, and there is so far no real definition for quality recycling, but I tried to make a definition by myself. And I think from the essence, it has or should have the most important elements. So quality recycling means it's economical viable recovery of various relevant contained materials with high yields in a marketable quality and meeting high environmental and social standards. And when we're talking about environmental standards, of course, this also includes energy and CO2 balance. And in a marketable quality means this comes back to what I mentioned before. We have to close the loop physically. So it doesn't help much if you produce a certain intermediate which nobody can make use of, even if on the paper you meet the requirement of legislation. You really have to produce something which finds its way into new products. And a good or a bad example in looking how circular we are today in reality, I selected here vehicles or end-of-life vehicles. This is a concrete example of Germany. These are numbers from the most recent statistic from Umweltbundesamt, so the German EPA. So every year in Germany, about 3 million cars are taken out of service, the registers. From these 3 million deregistered cars, about 500,000 cars, 500,000 are recycled in Germany, with an average age of 20 years, an average mass of 1 ton. And the cars which are recycled in Germany barely include the premium brands, because they are going somewhere else. We have a lot of exports of end-of-life vehicles. About 350,000 of these cars are officially exported out of the EU, so there we know where they are going. Many of them are going to Western Africa. Then we have about 500,000 cars where we even don't know where they are going. And I mean, we are talking about a car, not a smartphone. So a car is a big device, but we don't know what's happening with them, which is not a good prerequisite for a circular economy. And about 1.9 million of German cars are exported into the EU, so also to the Netherlands, to Belgium, and so on. But the question is what's happening afterwards. And we know that in Rotterdam, in Antwerp are big harbors, and a lot of cars are also shipped from there. So in a nutshell, and there are similar figures for the whole of Europe, a very significant part of end-of-life vehicles from Europe are shipped out of Europe and to other areas. And of course, in these areas, some of them are used for a couple of years, which is fine. But in most cases, at the end, there is no high quality recycling. There might be some kind of recycling, some steel recycling, some copper recycling. But most of the other technology metals are not recycled because there's no infrastructure to do so. If you look at the legal obligations, we have the ELV directive on the European in Europe, which calls for 95% recycling, including energy recovery, and 85% of physical recovery. So the recycling waste, and this is based on a mass balance. But what you need to know is that this 85% recycling requirement is only accounted for this 500,000 cars which are recycled in Germany. So all the ones which are exported don't count for the recycling rate, which means on the first glance, and if you discuss with the automotive industry, they often said, well, recycling works perfectly, we meet the targets and so on. But if you make really the calculation, if you take 3.1 million and multiply it with 15% and then with the 85%, you end up at 30% and circularity rate. And of course, this is not the circular economy which we want to achieve. And small side remark, the calculation even is not including the complete final process, but it's only the input in the final process. So of course you also have additional losses in the final process. So this means for cars, and cars is just the example, this is true also for electronics and for batteries, for many other products. On the one side, we are meeting high recycling requirements from legislation on the paper, but in reality, we are not circular at all. And in this context, it's really important to understand how recycling works. And this graphic here is in principle valid for all kinds of products. Recycling never is just a single process. It's always a chain of processes. So it always starts with collection, and often collection is the weakest point in the whole chain. Then you have pre-processing, which is usually a combination between manual and mechanical separation steps, physical sorting. And then you have end processing, and in the case of metals, end processing, these are chemical metallurgical processes. And the more you go to the end of this recycling chain, the more you need specialized plants, and also the more economies of scale play a role. And of course, if you have such a chain, in principle, at all steps, losses do occur. And we have to distinct here between avoidable losses and also unavoidable losses. And here just some reasons for losses. So of course, it's obvious if products are not collected, they also cannot be recycled. What we see often, especially for cars and electronics, they are collected, but after collection, they're somehow escaping the system, called a dubious export. Then, of course, you have losses in pre-processing because certain metals go into wrong fractions. And of course, also you have losses in end processing. You have residues like flue dust, like slags, and so on, which also include metals. And if you make a calculation, and this is now more concrete, this is, for example, looking at how good are we in recovering gold from end-of-life electronics in Europe. And I think these numbers are pretty close to reality, maybe even still a bit optimistic. If we have a collection efficiency of 50%, a pre-processing efficiency from a gold perspective of 70%, then even a very high metallurgical efficiency of 95% doesn't really save us, because if you make the multiplication, you end up with about 30%. And only this 30% is a physical circularity rate, which we can use to become more independent and so on. And the recycling rate always has to be the product of the pre-processing yields and the end processing yields. And also here you see 70% times 95% is 67%, which is not that high anymore. But as mentioned before, the biggest challenge usually is the collection rate. So what are the main drivers for recycling? It's certainly economic value. If you have something very valuable, then the chances that it will be recycled are much higher than if you have little value. Business models and incentives like deposit schemes or also leasing models, and of course legislation and the enforcement of legislation. And what are the main challenges? Main challenges are insufficient collection, dubious exports, complex products, inappropriate design, substandard treatment. And why substandard treatment? Because it's usually cheaper. Good recycling is more expensive than bad recycling. So if nobody really looks what's happening, then of course people select the bad recycling. And this overall leads to high metal losses, but of course also to significant environmental damage. So if we want to keep materials in the loop, we have to fulfill two requirements. And the word circular economy already has both in the expression. The circle represents the physical part of it, and the economy, of course, the economical part. So the physical part means we have to really reapply recycled materials into new products. Only then the circle is closed. And the more complex a product is, of course, the more challenging it is to close the circle for many materials inside. And the economical requirement simply means that you have, it needs to be economically viable. So if the total costs of the recycling chain, collection costs plus pre-processing costs, plus metallurgical costs plus compliance costs are higher than the intrinsic value, recycling will not take place unless somebody is willing to bridge the gap. And the gap can be bridged by recycling fees, can be bridged by deposit rates and so on. But we have to see this economic dimension, and we need from the legal side, from authorities, frame conditions to help to bridge this gap. This also means that not any recycling is fit for a circular economy, but we really need high quality recycling processes. And as with our products, we are not limited to Europe. We produce products which we are then exporting to other parts of the world where we are used. Also, the circular economy on the long term has to be covered in a global context. And we have to look at streams out from Europe, but also streams coming into Europe. What are the current barriers to closing the loop to a circular economy? Although we talk a lot in legislation and also at companies now, circular economy is one of the big buzzwords. Everybody is circular if you go to the websites, but if you have a closer look, there's still room to move. If you look at most consumer goods, we still are very linear, and the life cycle is disconnected at the consumer. We have a production chain starting with raw materials production, then part component production, then you have the OEMs, then you have the retailers, and there still we have a very traditional downstream upstream interaction between the players. Then we have the consumer or multiple consumers, the first user, the second user, and so on. And then we have an end-of-life chain, starting with, for example, municipal collection, reuse, or pre-processing, and end processing. But at the moment, there's a missing link. It's two parts of the circle, but the circle is not connected. There's a missing system approach. There is little overarching collaboration. At the moment, in most cases, with the traditional business models, a manufacturer produces something and then sells it into the market. There is no incentive for a manufacturer to produce something which is durable, well repairable, and recyclable, because there are no economic benefits for it. In many cases, there is little knowledge and unfortunately also little interest on the fate of products after the distribution, especially after they have left the warranty period. And also most processes, tools, and financial systems in companies are still tailored to linear business. If you then look at the end-of-life chain, also today there is still more focus on the cost and prices and on the quality of recycling. We have so-called extended producer responsibility systems, but so far they don't reward a comprehensive and good recycling. There also is a high cost pressure in the system. Most OEMs focus so far on legal compliance and image, but less on generally circular business models. I already mentioned that the reported recycling rates in legislation do not reflect the physical truth. And this is very interesting with a battery regulation, which just had been introduced. There it's the first time that we have specific required recycling rates for specific metals. So recycling rate required for cobalt, for nickel, for lithium, and for copper. In all traditional legislation, we have a weight-based recycling rate, which means 85% of a car needs to be recycled, which, if you translate this, it also means you have to focus on the mass metals, or mass materials like steel and glass and so on. But whether we recover some grams of gold or indium or gallium doesn't count for the calculation. So, and this is the last slide. If you really want to become circular, it requires fundamental changes in the way we develop, design, produce, distribute, use, and recycle products. Circular economy means both recycling and approaches to lifetime extension. But in the end, hopefully after a long life, after a long service life of a product, we need recycling to physically close material cycles. Companies have to adapt their business models. We need new forms of stakeholder collaboration. Upstream, downstream doesn't make sense anymore. And the cycle, everybody is at the same time the customer and is the supplier of everybody. So we should think more about downstream collaboration. Also, this may be more something for the discussion. I personally believe that the product system services Product service systems could be a bit the game changer to become more circular. And the key challenge is especially for consumer products. So in a B2B environment, circles can be closed quite well. But in consumer products, it's much more difficult. We need more transparency on products and material flows along the entire life cycle of a product. Here, product passports can play a role, and also, again, for traction batteries, passport will be developed. It can be a central tool to get there. We need appropriate legal frame conditions and also indicators to measure how circular we are. And we certainly should focus the circularity strategies for green and clean products like electromobility, like photovoltaics, like windmills, and so on. Because by definition, a green product cannot be green if we don't manage to close it. Yes, thanks for your attention. It was a bit longer than the half hour, but I still think we have some time for discussion.
Thank you, Chrisian. I see a lot of clapping hands, so that's a good sign always. But thanks for an excellent presentation. And raising. I at least have some questions, but I'm sure there are also questions from the audience. So if you would like to raise a question, just raise your hand. Elise.
Yeah, thank you, Chrisian, for the very nice presentation. I have a question regarding, because everything was pretty clear, the link between the stakeholders that is missing. Sorry, I'm going to talk to the camera instead of the big screen. I was wondering, and more in the practice, what does Umicore do to give feedback to designers or other important stakeholders? I mean, you are the end of the chain, so you recycle the product, so you see what's wrong in the design, what could be improved. Do you have an active part in giving feedback to designers or waste collectors or other stakeholders?
Yeah, I mean, the feedback to waste collectors, this is ongoing since years, because this is a bit the same branch of the part. So this is end of life management, and this works quite well also via associations and so on, which doesn't mean that there is not still room for improvement. But there is a good interaction between especially waste management companies, preprocessors, and metallurgical companies. And in many cases also we have the same common interests. I mean, in the increasing collection helps everybody. No? The interaction with the manufacturers is a bit more difficult because often we are asked about recycling or recyclability if a product already is developed. And then we say, yeah, it's a bit late. It would have been good to have certain discussions earlier. There are some very generic messages, and this generic messages me and other colleagues within Umicore are giving also since many years at conferences, at association meetings, at policy events, and so on. And this is design for recycling is maybe difficult because the product has different functions, but at least we should design for disassembly, and this helps both repair and recycling. And yeah, but if you look at reality, a smartphone, a tablet from a both repair perspective or from a recycling perspective is the worst what you could do. So yeah, we have to see. It's challenging, especially in consumer products. We are looking for this dialogue. There also have been meetings, but so far, in few cases, really led to real improvements. It's much easier in the business-to-business environment. And with many of our products, we are in the business-to-business. No? Even we sell catalysts for the chemical process industry there, or also catalysts for fuel cells, for hydrogen electrolysis. Their recycling is already part of the sales discussion. So there it works well. And we just published, by the way, from the IRTC a paper, which is also mentioned here, which is the Simplish et al., which looks a little bit into the advantages you can have in certain business-to-business environment and what can be learned from this for a business-to-consumer environment.
Yeah, I guess one of the difficult things is that for you as Umicore, it's an improvement of the process. I mean, if you're the input, the quality of the input is better, then basically you make more profit, or the recycling becomes easier. But for the designer part, it's an investment to make a different product. I guess that's also a bottleneck.
Yeah, it's I mean it's and this again is a very good that it's the first time addressed in the draft battery regulation. So far we had waste legislation, but no product or life cycle legislation. The battery legislation really has a life cycle approach. And if you have really a life cycle approach, then you also start to look at the total cost of a product. And then if you understand that recycling is an intrinsic part of the cost of putting a product on the market, then there would be a benefit for better design. But as long as recycling is just outsourced to some waste managers, yeah, as I mentioned, there's little incentive to do something which is recyclable.
Yeah, thank you.
Okay, Maarten.
Yes, Christian, thank you for an interesting presentation. I have a follow-up question on the question of Elise, maybe the question a bit turned around. The product designers are currently reducing materials intensity of critical materials often in a lot of products. For example, EV batteries containing less cobalt. I wonder what that does to the recycling process, but because I can imagine that makes recycling more difficult and maybe reduces the incentive for recycling.
Yeah, no, interesting point, Maarten. Of course, if you reduce value, the incentive to recycling is smaller. No? But so the best smartphone would be a smartphone not with 250 milligrams of gold, but with 250 grams of gold. No? So then it would be definitely collected. But of course, it doesn't make sense on a resource efficiency point of view. So I think raw materials efficiency in producing products and in developing products is extremely important, and we have to continue this way. Probably the game changer will be the very moment we really factor in recycling as part of the product life, which means if there is less value, but by definition at the end of life the product needs to be recycled, okay, then there will be some kind of fee, of deposit or whatever to pay it. And it sounds a bit strange, but if you look at our household waste, I mean, all of us are willing to pay a certain fee every month to getting rid of our household waste. And the same should happen also for products. And the point is that we still mostly think about microeconomic benefits. But of course, we also have to think about the macroeconomic benefits. And if we are better in recycling, and if then we become more independent from imports, if we then need less mined materials and have a much lower CO2 footprint, of course, this directly also reduces macroeconomic costs at the moment we pay from other channels by taxes and so on. So we have to see this more in a holistic way. But it's still process, no? Also a mindset which needs to be done.
Absolutely, yeah. Okay, Sander.
Yes, thank you. So, Chrisian, I have a question about, well, one of the concluding remarks that you made about, well, the greener and cleaner products, well, as well for the manufacturers. They, of course, have incentives or want to claim to their, well, to the consumers that their product is indeed recycled or fit for recycling. What would you say is a better metric to look at, well, recyclability at the end of life, or actually the recycled content in the product itself?
Both and even more. Let's start with recyclability. The fact that the product is recyclable doesn't mean that at the end it will be recycled. It still can be exported, it still can end up in a drawer and so on. So recyclability is a kind of basic requirement, but it's not sufficient. Recycled content is an interesting approach, but we really have to carefully look how it is used. Originally, recycled content was more coming from the plastic side to generate incentives to use recycled materials instead of virgin materials. The driver there was a little bit that for plastics, often the quality of recyclates is a bit lower than from virgin materials. So this incentive was used to pull more recycled materials into the product. In case of metals, you need this. Usually, you don't need this quality incentive, because if a metal is recycled, it has the same physical chemical property and also traded at the same prices as it's coming from mining. But of course, if you have recycling content requirements also for metals, it helps to get good definition of what is recycled, because even if something at the moment is only recycled on the paper, but not in physical reality, because it's still a reality, if you want to claim recycled content for your product, you need something which is finished from recycling, which has the right quality. So this is one thing. And if there is a big need for having recycled metals in products, of course, this also has a pull effect. This could make manufacturers more think about how to keep end-of-life products in the loop and avoid exports and things like this. What we have to be careful about is that we don't use recycled content for greenwashing. And I give you an example. We all know that beverage can recycling, aluminum beverage can, for example, works very well. There are deposit systems, they are returned, and you have a very high recycling rate for aluminum. Recycling of smartphones doesn't work that well. There are a lot of smartphones with aluminum cases. Of course, a manufacturer easily could get recycled aluminum from beverage cans and put it on a smartphone and then say, now I have a recycled content in my casing of 100%. You could do the same with recycled gold from jewelry, which is also working very well, and you put it in electronics of a does this make the smartphone greener? No, not at all, because then this aluminum, this gold, or this cobalt you might take from hard metals, and then instead of from a battery, is then missing at the other application. Yeah? So if we look into recycled content, then we should close the loop, or should prove the recycled content that it's coming from more or less the same field of application. And this is at the moment one point which is still under discussion. It's not still clear under the battery regulation. There is a recycled content target, which is good, but it's not clear how to calculate and where it's coming from.
Yes, thank you.
Okay, Ming Ming.
Yeah, thank you for the very thank you for the question, for the very inspiring speech. And I have just one question. Would like you to explain a little bit of the explanation on your final remarks. You say the product service system can be the game changer, because so far we see clearly it's the consumer consumption part is the barrier, and the consumers' option are, I think, are framed by the production system. So it's how the producers is offer the options on the market, so can influence the consumption scenarios and choices. So I don't know if your company have already think about which information we can provide to the consumer. How can we help to bridge this barrier to make this circular physically really can happen?
Yeah. I mean, specifically for Umicore, the point is we hardly sell any products directly to consumers, because our Our customers are OEMs, chemical companies, and so on. Of course, we provide very detailed information to our customers about the composition of our materials and so on. But maybe coming back to the initial part of your question, why could product service systems be the game changer? At the moment, a manufacturer, and we mentioned this, has little incentives to make something repairable, durable, recyclable, and also to recycle it. And in many cases, and cars and electronics are a good example, they have no clue where their products are after a couple of years. So even if by legislation manufacturers are obliged to take something back, they have no grip on their products. And then let's, for example, use the example of an electric car or a battery in an electric car. If in future we would not sell the car or the battery anymore, but would just sell the service of using a car, at this very moment, it would be in the direct interest of the manufacturer to make his product durable, repairable, because the longer he can lease it out, of course, the more he can get the lease rate. So this is one part. So there is an inherent incentive for a better design. Secondly, it also means that we as customers, of course, immediately would return the product if we don't need it anymore. Because otherwise we just would pay a lease rate, but don't have anything for it. So this would end smartphones in drawers and so on, or products just parked somewhere and not used. And lastly, it would turn a B2C system into a B2B system, because then the car manufacturer or the leasing company would be the owner. The point is they need to be the owner to the end of life. For many company cars, they already leased for 4 years, for 3 years, for 5 years, but afterwards they are sold into the open market. And of course, then it doesn't help. But if this really would work to the end of life, then the fleet operator also would have a critical mass of products. He would have his own products, so he knows very well also what is in, and he could directly make a contract with a waste management company, with a recycler, and even then have physical turning around the loop. So can get access to really recovered metals from his own products. He could prove what is the real CO2 footprint of it, and so on and so on.
Thank you very much. Very inspiring. I think along this way. Thank you.
And a bit on these thoughts you find in the second publication there.
Yeah.
So they have the link. So it's really an interesting read.
Thanks. Okay, I think our final question of the day is coming from Kumar.
Hi, thank you for the informative presentation, Chrisian. And you mentioned an important issue while your presentation, that is regarding the collection of these devices or technologies that really have these rare earth elements or critical metals. So what do you think would be beneficial, or would be an approach that a company can take to facilitate these collection processes? Because if we don't, like you mentioned, that if we don't have a strong collection point, then we can have high recycling rates, but it doesn't really matter, because at the end, we're not extracting or recovering a lot of metals. You said that for business to business, it's a bit easier. But for instance, in wind turbines, we have neodymium magnets, but those magnets are less than 1% of the whole weight of the wind turbine. So what do you think would facilitate the collection of those magnets or critical metals.
Yeah. So give first a general answer, then specifically on the wind turbines and on the magnets. So from the general answer is, of course, what we just discussed, leasing models, product service systems definitely would facilitate collection, because then the user would bring the product back. Secondly, for some consumer products, I personally think that indeed for tablets or for smartphones, the deposit system would help. It works pretty well for beverage cans. Why not for smartphones? Because all other approaches over decades have not really resulted in any improvements. And then, of course, it's also a question of having appropriate infrastructure and having mechanisms in place to stop end-of-life products leaving a system boundary without being known, so control and harbors and so on. In the specific case of windmills and magnets, first, the big advantage of a windmill is it's stationary. So you build it somewhere and then you know where it is, and it doesn't run away. And usually, of course, there's a good construction drawing and so on, so everybody knows or can know what is in and where the things are placed and so on. And then the producer of the windmill, if he wants to become circular, he should offer. And then usually he has a service contract anyway to maintain the windmill. So he should offer. If a motor exchange, then he takes back the magnet. He could then have also a critical mass of magnet. Of course, he needs a disassembling process for this. But then he could look for a recycler of magnets and find a solution there. But it needs to be part of the business approach right from the start. This is, I think, the main change we have to do. Traditionally, you develop a product, you sell a product, it's placed on the market, and then maybe one day somebody thinks about closing the loop and recycling. No, it has to become an integral part at the very beginning.
Okay, thank you. And I think that's a really interesting topic, and I was also really triggered by your numbers for cars in Germany, and I'm just thinking about what that would mean in terms of if all these cars would be EV cars with batteries on board and magnets. I mean, that would really be a disaster in terms of recycling and materials, that are basically gone to unknown destinations. And I think the same is happening for solar cells that are now being replaced by more efficient solar cells, and then the old ones go on a ship to somewhere in a developing country, and you never know what happens at end of life there. So I think this is really an issue we need to address with huge amounts of materials now being invested in the renewable energy system. I think we should give a lot more attention to that, I think. Yeah. So thanks again, Christian, for an excellent talk. Thanks for answering all our questions. I was really happy to have you in this series of talks. Thanks again also to all the participants and your active contribution. So thanks a lot. And I hope to see you next time. And Christian, hope to see you somewhere soon in real life.
Yeah. No, thanks, René, and thanks also for the invite. It was interesting for me as well. I sent yesterday, Silke, a PDF of the presentation, and it has a relatively big number of annexes which are going specifically into the battery regulation. I didn't touch it just for time reasons here, but it could be interesting to have a closer look at this as well. And of course, you can share it within this group.
Excellent. Thank you very much.
Bye. Have a good day.